So we've been seeing how to do feature selection, which is actually throwing out some features and keeping other features, so keeping a subset of features. Feature extraction is a bit different in that we actually transform the features, our original features, into new values, new features that we're going to use subsequently. So we're going to see some different ways of doing feature extraction. These are only two examples. I'm going to talk about principal component analysis and self-organizing maps. There are actually many different ways of doing feature extraction, of doing dimensionality reduction by transforming the features. But what I want to show today is just the general idea of why we want to do feature extraction and the different ways that we can do it. But basically, the fundamental difference between feature selection and feature extraction is that in feature selection, we want to select a subset of features. So basically, if we have a table, we want a subset of the columns. In feature extraction, we are creating new values by transforming the original features in some way. So the purpose here is to derive some useful features. It can be also to reduce dimensionality, but often it is just to extract, to obtain some useful features from an original set of data that is not particularly useful. For example, if we have images, we have maps of pixel values, and these by themselves may not be particularly useful for what we're trying to do. There are too many of them, so we may want to reduce that to some specific measures like entropy or things like that in order to extract some useful features. An example of this would be the banknotes example that you did for the first assignment. So the original data set was extracted from the scans of the banknotes, but by measuring entropy and some wavelets parameters. So you had some specific coefficients drawn from the image. You can do that with words, with text, with sounds, frequencies, and so forth. So in general, if you have unstructured data, you usually need to extract some features in order to use these classical machine learning algorithms. You can also use feature extraction to reduce the dimensionality. So instead of reducing dimensionality by throwing away features, we want to reduce it by combining features in a particular way that leaves us with fewer values, but with as much information as possible. So this is very dependent on the kind of data that you're dealing with and the type of problem you're dealing with. So we're not going to look too much at details, but I'm going to give two examples, PCA and self-organizing maps, just to give an idea of how to do these things, how to do feature extraction, and why we want to do it. So principal component analysis is not a particularly useful method. So for machine learning in general, it has a few drawbacks, but is a classical example of feature extraction for dimensionality reduction, and it's still useful for things like projecting your data and to help visualization, things like that. So the idea here is that we want to find, if we have multidimensional data, we want to find an orthogonal set of vectors that can be ordered in the way that the first vector retains or is along the direction of the largest variance of our data. The second vector is perpendicular to the first one and along the direction of the most remaining variance after we project on the first one, and so on. So this way, if we have these vectors and we can rank them, we can select a number of them. They will form an orthogonal base, and we can use that to project our data into a lower dimension, retaining as much variance as possible with this linear transformation. So basically, you can imagine that we are rotating our data and projecting along some axis in a way that maximizes the variance that we retain. So we can reduce dimensionality by finding these vectors and keeping only the first k of them. So let's see a simple example. Let's imagine that we have this three-dimensional data set. The points are more spread out along this diagonal here, and we want to project this into 2 dimensions with a linear transformation. So basically we are rotating everything and projecting, but we don't want to lose variance. So we want to retain as much as the dispersion of the points as possible. So we can imagine that if we project everything along this axis here over on this side, we will get all the points jumbled together in the smaller region. So this would not be a very good idea. On the other hand, if we take advantage that they are spread out more in this diagonal and we project them into this plane like this, for example, then we would have a bigger spread on our data points. So now the question is how we can compute these vectors. So the first thing we need is this scatter matrix. So the scatter matrix is basically a multiple of the covariance matrix, and if we have our data in n dimensions, this will be an n by n matrix where we have all the products of the first coordinate by itself, the first coordinate by the second one, and so forth. So all the combinations of features, we have these products. And the products are computed by centering everything on the mean. So this m vector is merely the average of all the different feature values, so the central point of our data. And now for each example in our data set, for each vector, we center it on that mean. And now we compute this matrix with all the products of all the features. So the first feature by itself, the first feature by the second one, and so forth. This is represented here by multiplying this column vector with this row vector, so the transpose of the vector, and it gets us this matrix. So the size of this matrix is the same number of rows and same number of columns as the number of dimensions in our data set. And we keep adding for all the different examples. And then we find the eigenvectors of this matrix. The eigenvectors are the vectors with this property. So an eigenvector of a matrix is a vector that when we multiply the matrix by that vector, we get a vector with the same direction as the original one, but just rescaled by some lambda parameter. And this is the eigenvalue for that vector. So basically, if you think of the matrix, you can use a matrix that has as many rows and columns as the number of dimensions of your points to do some transformation on your points. So you can imagine the eigenvectors as being those directions in which this transformation only stretches the coordinates and does not rotate, does not change direction. So basically, we are finding the vectors where this matrix, this scatter matrix here, does stretching but without rotation. And these would be the eigenvectors for the matrix. And now we can choose the ones with the largest eigenvalues, and we get the largest possible variance under this transformation. So this is just an example with code. We are going to use NumPy. We compute the mean points of our data. So this is the average of each feature. And now we create a 3 by 3 matrix with zeros because our problem is in 3 dimensions. So our scatter matrix will have 3 rows by 3 columns. And now we add all these products. So we are going to center each vector by subtracting the mean, and then we're going to reshape it as a column vector and do this dot product between the vector, which is a column, and the transpose, which will be a row. So basically, this operation here gives us the 3 by 3 products of all the combinations of features there. And so we keep adding that to the scatter matrix, and now we use this linear algebra module in NumPy that can compute the eigenvectors here. So we get the eigenvalues and the eigenvectors. The eigenvalues are these lambdas here, so they give us a magnitude of how much the matrix stretches in those directions. And the eigenvectors are these columns in this matrix. So here we can see that the first vector is the most important one. This is that diagonal where the points have the greatest spread. Then the third one is has the second largest eigenvalue. So we can use these two vectors to project our data and retain as much variance as possible with this linear transformation here. So these are the three vectors that we got here. You see that one of them is aligned with the largest dispersion, and then the second one is aligned with the greatest variance that remains once we discount the first direction, and so forth. So projecting everything here, we can create a matrix with the two vectors and then simply multiply all our data sets with that matrix. So this is basic algebra, but you can do all these rotations, these coordinate transformations by multiplying the matrix. And we project everything into 2 dimensions. Then it's just doing the plot, and I'm setting an equal aspect ratio to so that the scale in the x and y axis are the same, so that we can see that the first eigenvector that we got is the first direction there that has the largest dispersion. So this is where the range is largest. And then the second one is the orthogonal one with the largest variance remaining. And so by picking these two vectors, we can project our data from 3 dimensions into 2 dimensions, preserving as much as possible of the variance in our data. Now, the reason why this is often used, PCA, is because it's very easy to use and apply, and it's useful to projecting data into fewer dimensions for visualization and so on. On the other hand, the reason why it's often not very useful for classification problems for machine learning is that in many cases the variance in the data is not well correlated with what we want to distinguish between the two sets. So suppose that in this data set one of the classes was here and the other was here. If we project over the largest variance, then we just mix the two classes together, and we are not finding the best projection to separate them. So PCA is very widely used. It's easy to use. You don't need to do things manually. This is just to explain what the procedure is. In the decomposition module, we have a PCA class that you can just specify the number of components, and then you fit your data, or you can transform, or you can just do fit transform and do it in one step. So basically, you can transform your data into a lower dimension with PCA just by specifying the number of components. So this is very easy to use, but sometimes it's not really, there is not a strong correlation between variance, preserving variance, and what we want to predict. So it's often the case that PCA is not very useful for machine learning. Now I'm going to give just one more example, because this one is related to neural networks, and it's more like a machine learning algorithm. There are many other ways of transforming data, especially for dimensionality reduction, but the idea here is not to give you a very exhaustive set of techniques, but just to give you the feeling, the intuition about how useful this is, and a concern for this kind of transformation. So a self-organizing map, you can think of it as an artificial neural network that has just one layer, but has a special topology. So you have each neuron has a set of weights corresponding to the dimensionality of the data set that we're using to train the network. But in addition, each neuron has neighboring neurons in this layer. So you can imagine that the layer is actually a two-dimensional matrix where each neuron is connected to its neighbors. And the idea is that when we are training, we are presenting examples at random, and we are going to check which of the neurons has a vector of weights that is closer to the example we are presenting. And this one, we're going to move it slightly to become more similar to the example we presented, and we're going to pull the neighboring neurons along, also changing them in the same direction by smaller increments. So basically, we keep the same topology of this layer of neurons, but we are adjusting it in our data space to the shape of our data set. So by training, we're going to start with small random numbers for the weight. We're going to present each example at random and check which of the neurons is closest to the vector for the example, and then we're going to pull slightly on this membrane in the direction of that example. And we keep doing this while reducing the learning rate so that things start to freeze eventually and no longer move around. So the idea is that we have these two topologies in parallel. We have the shape of our data in some multidimensional space, and our neurons have also a vector of values in that dimensional space. So we can measure the distance between each neuron and each example. But the neurons are also laid out in a two-dimensional topology by having neighboring neurons. So when we find one neuron that lies closer to an example, we move that neuron towards the example, but we also pull its neighbors slightly in the same direction. This means that we are fitting this layer of neurons in our multidimensional space while keeping the same topology, like stretching a rubber membrane into the shape of our data. So when we want to visualize our data in two dimensions, then we can use this topology, this two-dimensional topology, represent our neurons and plot our data in those two dimensions regardless of how many dimensions it originally had. Okay, so let's see a simple example in order to understand this better. We have a data set of colors. Colors are in three dimensions, red, green, and blue. So black would be 0, 0, 0, blue would be 0, 0, 1, and so forth. We have all these combinations to create the different colors. And this data set lies in three-dimensional space because we have combinations of three channels. We want to project this into two dimensions with a self-organizing map. So we're going to use this mini-SOM library. This is not part of Anaconda, but we are not going to use this in the tutorials. This is just a kind of demonstration here. But it's easy if you want to just download one of these implementations and test it out. So the important things about this mini-SOM class is that we can initialize it by specifying the size of the layer that we want. So how many neurons in the horizontal and vertical dimensions, and the size of the input. So in our case, our input will have 3 dimensions, so it's size 3, and we can specify a number of neurons in this membrane in the self-organizing map. Then sigma is a parameter for how much each neuron is going to pull its neighbors, and the learning rate, it's the starting learning rate, and it will reduce gradually over the training. Then we have this method to randomize the initial weights, and then to train a batch a number of batches of examples. So each pass through our data set will be repeated this number of iterations, and the examples are presented at random to the network. So we're going to create our self-organizing map with 30 by 20 neurons, and we're going to train with our sample set of colors, doing 10,000 runs through all the sets. So this will gradually organize the self-organizing map, and will reduce the learning rate so that it will end up freezing in a particular configuration. And now this is just to plot through this range of colors and see which of the neurons in the self-organizing map is the closest one to that particular color. So this is the winner neuron, it's the one that is closest one, and we draw there the name of the color. So this is the result that we have here. We projected this 3-dimensional space of colors, of red, green, and blue combinations, into 2 dimensions by forcing the self-organizing map to stretch in this data set of colors. And now we can plot each of the colors that we have by associating it with the neuron that is closest to that color, and so plotting it in this two-dimensional space. So the original space of our data can have any number of dimensions. It's not important. The self-organizing map usually has 2 dimensions, and it can help us project the data here, keeping these 2 topologies synchronized. So the topology of the map itself, which is this 2-dimensional table of neurons, and the topology in the space of the data that is given by the coefficients in the different neurons. So in this case, I'm using the coefficients in the neurons to draw the colors. I use the red, green, and blue values there to represent the colors, and this is how the color space will be projected into dimensions using this self-organizing map. So this is the general idea with a simple example. Now let's see a more practical example of why we need feature extraction and how we can use self-organizing maps to help visualization. So this problem is we want to try to organize data, look at different countries according to their patterns of development. So we're going to look from this site, Gapminder. We're going to download data on 4 different indicators. So GDP per capita, this tells us over the years how the gross domestic product of the country evolved. Life expectancy, infant mortality, and employment for people over 15. So we have these data organized by country. The data, each of these indicators comes in a different Excel file, and we have the countries in each row, so the name of the country, then we have the years and the values for the indicators. But note that there are many missing values here, so we don't have the same number of values for all countries. And if we plot things, also different indicators have different ranges. So this is an example for Portugal. We have estimated life expectancies here below 1920 or something like that. Then we have actual measurements more recently, some projections to the future. We have here only a small range of years for unemployment data. We have gross domestic product and infant mortality and so on. So you see, this is not a very clean data set where we can just have a specific number of features for a country. We will have to extract those features from this data. Also, different countries have different numbers of data points and different ranges, so for the United States, China, and so on. And so we cannot simply put this in a table and just feed it into some machine learning algorithm. So this is an example in practice of why we may need feature extraction. We may need to transform this data into something that we can put in a table and assign a set of values to each country. So one way of doing this is to fit curves to these data sets. So let's suppose we're going to use polynomials of degree 3. So we have 4 coefficients for each of these curves. Since we have 4 different indicators, if we fit one polynomial to each of these sets of values, we will have 4 polynomials to describe each country. These 4 polynomials will describe how the country evolved over the years in all these 4 categories, on all these 4 indicators. So with 4 indicators and 4 coefficients for each polynomial, we have a total of 16 dimensions. But at least once we do this, then we have a set of descriptors for each country that is always the same size for all the countries. So now we can use a table and go into the classical machine learning algorithms we saw so far. So these are examples fitting for example, for Portugal, the gray there is the set of polynomials for all the countries, and then we have here for unemployment, here for life expectancy, infant mortality, GDP, and so on. So we can do this for each country and get a set of 4 polynomials that describes the evolution of these indicators in each country, and we use these 16 values, so the 4 coefficients for each polynomial, as the description vector for each country. This will be the features associated with each country. Okay, so now we have we did feature extraction. We have each country described by 16 values, and we can compile a table with the same descriptors for all the countries. Now we want to visualize this. And we cannot easily visualize how the countries are distributed in 16 dimensions, so we need to project this into lower dimensions. We're going to use self-organizing maps. We're going to train it with our data, and then we're going to label countries with some countries just to see how they are distributed in this projection. Note that this part is unsupervised learning, even though we used a bit of supervised learning to fit the polynomials, so this is just basic regression. Now what we want to do is see how the countries are organized depending on their patterns of development. So we are not trying to predict anything specifically, we are trying to understand the data better, and this is an example of unsupervised learning. So we're going to train the self-organizing map and then label the countries there. So this is just, we create the self-organizing map with 30 by 45 neurons. The dimensionality on the data space is features is 16, so these are all the coefficients, yes? You can try, there is no fixed recipe, but usually if you use much more neurons than you have data, then you just lose time computing, and probably is not very useful. If you use very few neurons, then since you are then plotting your data on the closest neuron, then some data points will be superimposed there. So that's basically a trade-off between the two. But mostly this is a similar, in many cases, this is a similar decision to the resolution of the plot that you want to make or something like that. So here we start with our self-organizing map. Now we train with all the descriptors for the countries. So in this case, I'm using again 10,000 runs through all the data. And then we can plot a few of them. So these are about 200 countries. If you plot everything, it's hard to see. So I just wrote a list of countries to plot into this file, and then I go through the countries there and plot each of them. So plotting the countries is in the position of the neuron that is closer to those descriptors. Another thing that we can do is to get the distance map from the sum, and this gives us for each neuron the average distance to the neighbors. So it gives us a measure of how stretched that rubber membrane is to accommodate the data set, because some neurons may be very far away from others in the space of the data, where in other places of the sum, neurons may be more close together. So I'm going to use that to color the map here. So this is the projection from 16 dimensions into 2. We can see here this white region is where neurons are very stretched out. So this point here is an outlier with respect to the others, and it forced the sum to stretch in that region. This is Qatar. Qatar has probably a very different pattern of development when compared to other countries. So it's out there isolated and in a stretched out region of the sum. Then we see here United States, Austria, Germany, Netherlands, Switzerland, Canada, Sweden, Portugal here, and then Kazakhstan. I don't know exactly what this means, but we are somewhere between Sweden and Kazakhstan. And then we continue here, Russia, Vietnam, Mongolia, Egypt, and so on. So this is how the sum organized in 2 dimensions, the different patterns that we got when we looked at the evolution of the different countries over the year with that data. So to sum up what we saw, so basically what we are seeing here is first, in many cases it's necessary to extract features because the data that we have is not really useful for just feeding into some machine learning algorithm. So in this case we had to fit those polynomials so that we could describe the progress of each indicator with a fixed number of parameters. Another problem in more realistic data sets is how we understand the data. So this is one of the major applications of unsupervised learning, is helping us understand the data or helping us transform the data into something more useful. So to sum up, feature extraction is about obtaining useful features by transforming the original features. This in contrast with feature selection, where we are just discarding some and keeping others. With feature extraction, we're actually transforming the data. And this can be very powerful because you don't need to apply it only to tables. You can apply it to images, to a series of data points, to sounds, to text, and so forth. So feature extraction is a very generic approach that is often a precursor to applying machine learning algorithms. So we didn't look at many different techniques because now it depends a lot on what data you're using, but we saw one very general one, principal component analysis, and we also saw self-organizing maps as a way of self-organizing maps are mostly useful for visualizing data, although sometimes they are also useful for used for feature extraction. So if you have things that are not very, the data is not very well behaved, and if you project everything into a self-organizing map, you can then use the particular neuron as an attribute where the data fell into. In this example for the countries, this is a more realistic example than the ones we've seen so far, where the data can actually be quite messy. You have missing values, you have different numbers of points for each example and so on. So you need really to extract useful features from that. So you can see more about principal component analysis and how to use that in scikit-learn. And also, we are not going to focus too much on self-organizing maps. This was just an example. But if you want to read more about it in Wikipedia, there is a nice entry there, and I took some of the images from there. We're also going to see the k-means algorithm further on, which is in a way similar to the self-organizing map, apart from not having that topology in the self-organizing map. So you can also think of self-organizing map as a clustering algorithm that tries to retain that bidimensional topology of the neuron layer.